Okay, hi everyone. So what we're going to talk about today is different challenges and existing efforts towards trying to create global flood forecasting systems. We're going to start with a short overview of flood forecasting systems, because I'm not going to assume you guys are all hydrologists. And then we'll move on to three major components and talk about what are the challenges to providing flood forecasts anywhere in the world, and then existing methods focusing on machine learning-based methods, but not exclusively talking about them. And I'll try to focus not only on successes that we've already have, but also on challenges that remain open, and try to encourage as many of you as possible to maybe work on this problem if you want to create a large impact. So why are we even talking about floods? So floods are both the most common and the most deadly natural disaster in the world. They are responsible for between thousands and tens of thousands of deaths each year and affect hundreds of millions of people annually. But on a more positive note, floods are also one of the natural hazards that are most easy to mitigate. As opposed to, let's say, hurricanes and things like that, early warning systems can be incredibly effective in floods, because floods often develop in a relatively slow manner, and if people know that it's coming, they know what they need to do to protect themselves, doing things like moving to higher ground, not driving their cars in dangerous areas, and so on, we can avoid over a third of all both deaths and economic damages. This is done both by kind of individuals protecting themselves as well as governments doing various efforts to mitigate the flood effects. And a few years ago, Google's crisis response team did looked into a broad set of different interventions and found flood forecasting to be the most impactful potential intervention that Google could do. In a separate investigation, the UN has also recognized floods as being one of the lowest hanging fruit in trying to prevent fatalities worldwide. So let's talk a bit about how flood forecasting systems work. We're going to talk only about three components, and this is going to be slightly simplistic, but bear with me. So the first thing we need for a flood forecasting system is to collect various types of data. And this data is not equally available around the world. One type of data that we need is weather conditions and weather forecasts, precipitation, temperature, and so on. These are often provided either directly by satellite measurements, or if we want to forecast towards the future, we have numerical weather prediction models, the same ones that we saw a picture of in Michael's talk earlier that are not at good enough resolution, as we've heard earlier. These perform reasonably well in some locations, but they're based on ground truth data. So in places where we don't have local measurements, for example, in data scarce regions, which is often in developing countries, we don't have enough information to make sure that these models are working well, and often they don't work very well. The second challenge is what we call stream gauges. And this is a good opportunity to mention. In this talk, we'll be focusing on what's called riverine floods, floods that occur when a river overflows rather than coastal floods or flash floods, and so on. Stream gauges are measurements that we have on the ground inside rivers that tell us what is the water level or the amount of discharge going through that river right now. And they are one of the few sources of real, reliable ground truth for hydrologic models. And these are incredibly scarce in most of the world. So some areas have a lot of them, but in the majority of the world, these are missing. And lastly, we need elevation maps or elevation models, which tell us what is the structure of the ground. That way we can know how water flows across its surface. Once we have these types of data, just to mention, that's obviously not all the data that we need, but those are kind of a few important components. Once we have that data, we can run what we call a hydrologic model. A hydrologic model takes as input various weather conditions, soil moisture, and so on. Weather conditions such as precipitation, as well as the basin conditions such as the soil moisture, and puts out and outputs the discharge along the river. So it tells us how much water is going to be in different locations throughout the river network. And to do so, it models various processes such as how much of the water is going to be absorbed into the soil and percolate down it, how much of that water will then be sucked up by plants and perspirated out back into the atmosphere, how much will be directly evaporated, and so on. Once we've run this model, the hydrologic model, that produces estimates for the amount of water along the river network, we want to run something called a hydraulic model. And yes, hydrologic and hydraulic is probably the two most confusing terms hydrologists could have found for these two models, but they're two separate models that do two separate things. The hydraulic model doesn't care anymore about these long-term effects of evaporation and transpiration and absorption, but instead, when an event occurs, when a river, let's say, is about to overflow, we want to know exactly what areas are going to be affected. We want to know exactly where the water will go. So we can ignore at this stage a lot of the things that we've modeled in the previous stage, but now we're very, very sensitive to even small changes in the elevation map or in the ground structure around us. We want to be able to produce from this hydraulic model a map that tells us what areas are going to be inundated and therefore what areas are going to be dangerous versus safe. So to conclude everything that I've just said, we can kind of define what we're doing here into three major stages that each feed into each other. First, we need to collect data on what's going on in the ground or what are our forecasts for what will happen in the next few days. Then we run that data, these weather forecasts and so on, we push them into a hydrologic model that tells us, let's say 2-3 days from now, how much water is going to be inside each river. And then using those estimates, we can push them into an hydraulic model, which tells us exactly whether the river will overflow, and if so, what areas are going to be affected. So let's take these in reverse order, talk about the challenges in each one, and how machine learning and other scalable methods can help. So the hydraulic model, as we mentioned, the goal here is to be able to give an accurate map of what areas are going to be inundated. So we want to be able to understand the river, and then once it overflows, to identify exactly what areas are flooded, as we can see here in this image. And the way we broadly do this is as follows. So the first thing we need is the elevation map, also called a digital elevation model, or a DEM. This is often produced using various satellite imagery. This is at least a more scalable way of producing it. So we either use radar imagery or stereographic imagery to get estimates of the height of the ground at each possible point. We then also need in real time to measure the water levels in the river or to forecast them towards the future. To be able to do this, usually this is done by governments, and they continuously monitor these measurements. Once you have both of these inputs, you can run the hydraulic model itself. This hydraulic model is just a finite element solution to the Saint-Venant equations, or the shallow water equations, which are actually a specific case of the Navier-Stokes equations that Michael has mentioned earlier, and actually a relatively simple case. We can even, for the types of events we care about in flood forecasting, we can even ignore the advection term there, leaving us with a fairly simple partial differential equation. But for this to work well, we have to assume that our data is accurate. And very often, it isn't. So while on the right we have kind of this goal that we mentioned before, in practice, the majority of the world is not mapped, or at least is not, maps for it are not publicly available at a resolution that suffices to do this kind of modeling. So what we see on the left here is the SRTM, which is kind of the standard used elevation map that is globally available. And the problem is that it is at such low resolution, at tens of meters, that we just completely miss, in this specific example, we completely miss the river. So not only are we not accurate in saying what areas are going to be inundated, but we can't even tell if the river is overflowing. It just looks as if the water is just pouring all over the map. And obviously, this is worse than useless. If we were to use this, we would be getting terrible results. An even worse problem than the low resolution that is globally available is the staleness of those same elevation maps. So this is a fact that I was at least surprised when I started looking into this, because coming from a relatively dry country, I was shocked that rivers can move. Apparently, some rivers at least move at quite a high speed. So what we're looking at now is over a 30-year period in which the river just completely moves to a different path. There are, of the rivers that we're looking at, about 30 to 40% of them, we can't even use the same elevation map from 2 or 3 years ago. The rivers, especially rivers that are flood prone due to these kind of violent flooding events, tend to move quite a lot. And a lot of the existing global data sets are incredibly stale. So for example, the SRTM that I mentioned before is from the year 2000. So obviously that leads to significant problems when trying to rely on it to be able to forecast floods. One solution to this that we've been exploring is what we call multi-asset spatial alignment. So instead of using these special techniques of stereographic imaging or radar that require specialized missions, satellite missions, to collect, and therefore tend to be A, expensive, and therefore low resolution, but B, become stale because we can't do them every year, we want to instead use standard optical imagery. So we know that there's a lot of optical satellites across the world constantly taking additional pictures. These could be used as if they're a single stereographic imaging system. Now the problem is that as opposed to stereographic imagery, we don't know exactly what is the kind of difference in their angles, right? There are completely different missions, possibly even with different types of machinery. But we can, using the images themselves, estimate both the angle at which the cameras are pointing, we need to kind of analyze how the light is reflecting off the surface. And if we try to estimate all of these things together, we can also estimate what is the surface geometry itself. This, of course, requires a lot of imagery. We can't do this just using 2 or 3 images because there's a lot of variables here that we need to disentangle. But if we do have a lot of imagery, usually the order of magnitude of tens of optical images, which, again, are constantly being taken regardless of this effort, this allows us to both achieve incredibly high resolution. We have about 1 meter resolution and vertical accuracy, but also allows us to annually update all of our elevation maps. So that way we can continuously provide good estimates with very little cost. So here you can see an example of the same area under SRTM, as well as under the multi-asset spatial alignment pipeline, which you can see a lot more of the minute details can be seen there. But what we're seeing on the right here is actually not yet what we need for flood forecasting. What we're seeing on the right is what's called a digital surface elevation model. So this tells us what is the height of the surface that the satellites have seen at every given point. But some of those surfaces are interesting to us, and some are not. Specifically, things like trees, for example. If we include trees in our elevation maps, we'll kind of our models will think that the flood will have to climb over the trees to be able to pass, and obviously that's not true, right? Trees have kind of a thin bark, but we don't care about the canopy that they have above. What we really want to produce is what's called a digital terrain model, which only includes the height of the terrain itself and not things that are kind of standing up on it. We do this using, time for at least the first mention of machine learning in this talk. We use the convolutional neural networks. We don't even need to do anything fancy like the inception models we heard of previously. A simple 2-layer convolutional neural network gives us pretty much all the results as accurate as we need. We train these based on locations where we know what the terrain model is. There's been surveys of the ground. For example, there's many of these such areas in the United States. And then we feed the convolutional network these surface models, and it can filter out those objects which it doesn't want to take into account. Just to mention, for flood forecasting, we have a specific need. So what we need is neither the DSM, the surface model, nor the DTM, the terrain model, but actually we care about some of the things, depending on how they interact with floods. For example, we want to ignore trees because a flood goes below them, but we want to include buildings because those in urban areas tend to significantly affect the flooding behavior. So this is equally easy to do as long as we have data sets that also label exactly what type of building or object we have in our training data, which indeed these data sets exist and therefore is fairly easy to train. So this produces these 3D models of the elevation maps. I think many people here are pretty used to these three models. We see them on Google Earth all the time. But just to mention, it's completely non-trivial to be able to do this globally at such a resolution. If you go on Google Earth today, you'll find that, if you look into New York, you'll find everything in minute detail. But if you choose a random spot across the globe, you'll have a much lower resolution. The fact that we can do this anywhere in the world with a 1 meter resolution is both new and kind of mind-blowing. And on the right, you can see here, actually the model, the same one I showed you before, is actually produced by the MASA pipeline and gets really good results. So now we have enough data, we have elevation maps that are accurate enough for us to be able to model at very high resolution. But there's still a challenge, because that high resolution requires a lot of computational costs. I think Michael alluded to this earlier. As we increase the resolution, the computational cost rises at, in our case, in a proportional manner to the cube of the resolution. The reason for that is that we're doing 2D modeling, and so we have 2 dimensions, 2 spatial dimensions, but then our time steps, so we're doing a finite element solution, so every time what we're doing is we're updating the PDE with, like, let's say 1 second or 10 seconds and so on. The time step that we can use so that these equations remain stable is proportional to our resolution as well, because the less area you have in a single cell, the less time until you'll need to update the cell next to it. So that leads to pretty high computational costs. For example, kind of top-end hydrologic models that are global today use about a resolution of 1 kilometer. If we want to be able to model globally at a 1 meter resolution, that is a 1 billion time increase in the amount of computational costs we will need to invest. And 1 billion, it's not 1 trillion, but it's still quite a lot. To do this, we're actually collaborating with the team that Michael talked about before, Michael's team and Stefan's team, trying to use convolutional neural networks to scale this up. So here, this is exactly the kind of situation where we care about the results at a slightly lower resolution. I don't need to provide people with flood forecasts down to the meter. I'm never going to tell anyone that it's safe in this meter, but if you go 1 meter to the right, it'll be dangerous, right? People don't work at those scales. We need, let's say, those forecasts at a 100-meter resolution. But to be able to successfully model it, we need to be able to model it at a high resolution. Otherwise, we get pretty bad results. So this solution of this data-driven coarse graining can be incredibly useful for us in scaling up these efforts. And this is exactly the kind of real-world application that Michael was alluding to before. We have a 2D model with a lot of noisy data, and we're hoping that these efforts can be useful in this case. What you're looking at right now is exactly the same concept, but just applied to the St. Venant equations instead of the other equations we've seen earlier. Now, there's another advantage to trying to incorporate more machine learning into these kinds of models, rather than these kinds of strict physics-based models. And what I'm going to talk about now is not something that we've done yet, but something that I think would be incredibly valuable to do. And that is if we could also incorporate into these models experience from the past. And let's look at the example. So this, we're looking here at Patna, which is an area in northeast of India that tends to flood quite often. And what we're looking at is an evaluation of a flood forecast. So let's see if I can, there we go. So all this blue area is areas that were flooded and that our forecasting system said will be flooded. The purple areas are areas that we've alerted for but did not flood. This specific forecast is a very conservative forecast. We're trying to over-alert rather than under-alert. We have several kind of different thresholds for these forecasts. And then the red areas are areas where we didn't alert but were indeed flooded. So both purple and red is bad. So I think each one here is 5 kilometers. I apologize, it's just from like my collab. But so this is 50 kilometers if I'm not mistaken, each 10. So let's look for a moment at the false negatives. So areas where an alert should have gone out and didn't, and these are obviously incredibly painful. The vast majority of these areas are in this kind of spot over here. It's much larger than the other areas. Other ones are relatively small, even though each one of them is bad. But this one is much larger than the other ones, and that one disturbed us quite a lot, because not only is it large, there's something very weird here. So in the other ones, you can see that there's the place where it was actually flooded, and then it went a bit further. But here, it's completely disconnected from where the river is. There seems to be no path at which this becomes flooded. And looking at this, we were trying to understand what was going on over there. And we were very conceited. We were like, surely our model is correct. Let's see what's wrong with the ground truth data that we're working with. So we thought maybe this is based on SAR imagery, the ground truth data that we produce. Maybe that SAR imagery is identifying certain crops as if they're flooded, even though they're not. Or maybe this was actually a separate event, so there was a lot of rain, and so there was like, this was unrelated to the riverine flooding that we were interested in. So we actually flew out to Patna, and we walked along this river over here. And over here, there's something called an embankment, which is used to prevent the flooding from reaching new areas, which is why we kind of can say pretty confidently that these areas are not flooded. But then we walk and we find that there's actually something called a sluice, which is a gate that allows the water to run through. So someone had opened the gate intentionally. This area is agricultural farmland, so in that sense, it wasn't terrible that we didn't alert there. But there was just somewhere here inside the embankment, there is a gate letting through intentionally a lot of water to be able to water these fields. Now that is a very challenging problem, because these things are not documented. No one can tell you where they are, at least not in an aggregated manner. And we can't see them from satellite imagery. We have no chance. It's under the embankment itself. One hope we could have is to be able to update our DEM, to update our elevation map, for example, to identify that there is at least, let's say, a hole there. Maybe we won't be modeling gates, but to say there's a hole in the embankment where actually the elevation is very low and water can flow. So just to mention, generally updating elevation maps based on historical experience is relatively hard. We have few events, and the DEM has obviously a lot of parameters, but these types of specific cases, these types of very small and specific changes could fairly easily be learned from past experience. The result of all this is an alert, which you can see here. I mentioned before that we have kind of more conservative alerts that try to over-alert, and then these are kind of the less scary yellow ones, as well as more scary red ones, which try to make sure that they're only alert in areas that genuinely are going to be flooded, and these are sent out. Just want to mention, this isn't the topic of the talk, but I feel like you can't talk about all of this work without saying why we're doing it. The idea, of course, is for this information to be used to prevent fatalities and other harms. And we're currently using three main strategies to be able to inform people. One is directly informing individuals through their phones, on their maps, and so on. Secondly is informing governments so they can do mitigation and relief efforts. And thirdly, we recognize that though Google is pretty well placed to inform people who are connected to the internet, we're not very well placed to inform people who are not connected to the internet. So we're funding local NGOs to find creative ways to quickly inform people who are not connected to the internet, mainly in rural areas. They have a long list of fascinating techniques, including people riding on motorcycles with flags in different colors that can tell people how dangerous the situation is, and so on, things that we would never have thought of. Let's move on to the hydrologic model. And just a reminder, the hydrologic model is the one that takes as inputs weather forecasts and ground conditions, and then forecasts how much water will be in different rivers along the river network. If we can produce such a hydrologic model, we can then plug the outputs of this model into the hydraulic model, and even 3 or optimistically 5 days in advance, be able to provide high-resolution forecasts and warnings to people. The classic way in which hydrologic models are built is using this kind of long list of physical processes, most of them represented through PDEs, which kind of interact with each other, and each one is modeled separately. And some of these components work really well. The hydraulic model that we just talked about is an example of that. We have a good understanding of the physics, and given enough data, we can just solve, we know what the correct solution is. But some of these models are not modeled well, either because we don't perfectly understand the physics, or even if we do, because the amount of data necessary to force define the forcing conditions of these models is just completely infeasible. Right? One example of that would be the absorption model. So the model that is responsible here, it's written as the part of the runoff processes. The absorption model tells you how much water is going to absorb into the ground rather than becoming kind of runoff to feed into the river network. For this, actually implementing the physics requires so much data about the soil that even in locations where we've gone and physically measured the soil ourselves, we don't have enough accuracy and resolution to identify the exact amounts. And these are replaced by these conceptual models. So these models try to imitate what a genuine physics-based model would do, but we all know that's not how the physics works. For example, you can model the soil by a series of 7 buckets, and each bucket is leaky, and it's leaking into the next bucket. Right? We all know the ground below us is not made of buckets, but this kind of gives us a simple parameterization of how the ground is going to behave. But once we're in the field of conceptual models, which we all know are not a genuine representation of the physics, and all we want is some kind of conceptual mathematical equation that approximates the processes that we measure and see on the ground, we think that perhaps at this stage, machine learning can do this better and optimize for those conceptual models or optimize for those function approximations better than these kinds of very coarse attempts of talking about buckets. So in these types of components, which I've marked here, we believe that a significant improvement can be made using machine learning. And a lot of this work is still early, but I do want to highlight some work done by Kratzert et al. Under the advisement of Sepp Hochreiter, who've been using LSTMs to model drainage basins across years. And they managed to show that they capture the behavior of those basins as well as existing hydrologic models. But perhaps more interestingly, they can train on specific locations and do as well on new locations that they've never been trained on, as well as classic hydrologic models can do when they are trained and are, or what we call in hydrology, calibrated on the single basin that they're trying to perform on. So their unseen, their test results are as good as, I wouldn't call it train results, but results on basins that hydrologic models have been calibrated for. We've been doing some similar work, not with LSTMs capturing the kind of long-term state of the basin, but rather using CNNs to try and capture the spatial structure along the basin. So instead of treating the basin as a single element, trying to understand what areas are more absorbative and so on. And we've shown that CNNs can also capture other aspects of the hydrologic modeling as well. There's still a lot of work to be done on this modeling. So one classic example is the fact that, currently I just mentioned we have one model that tries to capture the long-term state and one model that tries to capture the spatial aspects of this model. But obviously, we'd want to be able to do both. But as we were working on this, we realized that there is a problem that disturbs us much more than the ineffective or the inadequacy of existing models. And that is the problem with data. So obviously, once we want to move towards machine learning models, or in general, data-driven models, we need a lot of data to be able to make that happen. But the problem is that the number of stream gauges worldwide is somewhat limited. It's about on the order of magnitude of 100,000. But it's also declining, so the number of stream gauges is actually, there are more stream gauges being decommissioned every year than there are being built. But perhaps most painfully, they are distributed in a very concentrated manner. So locations like the US and Europe have large amounts of stream gauges, but the vast majority of the world does not have functioning and publicly available stream gauges. And that's a big problem because the models that I just mentioned before, their success currently does rely on a lot of kind of local parameters. They do not generalize well enough yet to completely different parts of the world. They only work well when you're talking about similar climates as the ones that they have been trained on. So the last thing I want to talk about is data collection. which is perhaps the least sexy of the three titles that I have, but possibly the most important. So as I mentioned, strain gauges are incredibly important input for us to be able to train these models. They're actually the source of the labels that we use to train them. In recent years, there's been a huge improvement in the amount and the quality of satellite data that's globally available. And I think all the rave right now is using what's called remote discharge estimation to try and replace the need for strain gauges. So instead of having a physical measurement device inside the river, you can try and estimate based on the large amounts of signals that are collected in space, try to estimate how much water is passing through that river. This work has been going on for quite a few years now. This is definitely not a new idea. And there's a long list of papers published on how you can use different signals to be able to estimate water. So, for example, you can talk about how microwave signals interact with water relative to how they interact with regular soil or different kinds of soil. And then based on those signals, you can analyze and understand exactly how much water you expect there to be in a different location. However, so far there's been relatively little research on aggregating multiple signals together. And we think there's a lot of potential in aggregating multiple signals together because these signals contain very complementary information. And I'll give an example. Let's say we're using optical imagery. So optical imagery is very high resolution and can relatively accurately tell us where, what is the surface area of the river. It's very easy from an optical image to see exactly where the river begins and ends. But it doesn't tell us information about what is the depth of the river, right? Looking at an optical satellite image, you have no idea. However, for example, microwave signals are, because microwave signals go through water, the signal that returns to the satellite ends up being proportional to the volume of water rather than the surface area, which obviously has a lot of information that optical signals don't. However, there are no high-resolution globally available microwave satellites. So they end up having a resolution of 1 kilometer or 5 kilometers, and then it's enough that a single farmer open up his sprinklers around the river, and suddenly the microwave signal tells you that there's 10 times the amount of water that was an hour ago inside the river. So obviously, utilizing both of these inputs would be useful in getting more accurate results. So we want to use machine learning to integrate these signals into a single estimate of the amount of discharge in rivers across the world and create an enormous historical data set to be able to improve hydrology in general. The problem is that machine learning requires lots of label data. Now we have, I said, about 100,000 strain gauges worldwide. Not all of them are available, but let's say tens of thousands of locations, which is nice. But each specific location has only a limited amount of measurements. Let's say you have, as many strain gauges have, only a single measurement per day, and you want to use satellites that exist only a few years, let's say optimistically 10 years, then you only get several thousands, and in some cases several hundreds of measurements for each location. And it's important to note that each location, if we're trying to train a model to estimate the amount of discharge in the river, each location is solving a slightly different task, right? For example, if you saw the same picture in 2 different rivers, perhaps you want to give a different result. So the idea is to try to be able, on the one hand, to learn from all of these different rivers at the same time, and yet address each river separately with the limited amount of data that he has. The way in which we want to do this is to create a complex global representation. Here we want to be able to use a lot of kind of modern machine learning techniques that require a lot of data, because globally we have a lot of data. But then add to that a local regression that will be fairly simple, just because we don't have a lot of data per each location. This concept of using a single global representation anywhere in the world is definitely not a new concept. One classic example of that is what's called the normalized difference water index. We have a pretty standard way of using multispectral satellite data to estimate whether a certain pixel or a certain location has water in it. But the idea here is to take that same idea and create a more data-driven index. So try to not only identify what the NDWI does, which is whether there's water here or not, but try to estimate the amount of discharge and to approximate this using data-driven methods. And secondly, we want to utilize the fact that we just have a huge amount of data to significantly improve the complexity and the accuracy of our models. So we have a bunch of results that are based on convolutional neural networks, but I think those are slightly less interesting because the story I'm sure you've all have heard before. We had a lot of data, we used convolutional networks, we got good results. I want to focus on some more of our theoretical work. And for our theoretical work, we're going to put aside the convolutional neural networks and assume for a moment that everything we're working with is linear. So we're going to assume we have a linear global representation, so just a matrix representing how we convert those images into some kind of latent representation, and then linear local regressions. I do want to mention that despite the fact that being linear obviously limits us, it might limit us less than people would think at first glance. So for example, using kernels, we can actually represent a pretty wide variety of functions using only linear methods. One extreme example of that is what's aptly named extreme networks, which allows us to do very nonlinear things, but still the part that the model needs to learn is linear. So all of these results will apply to all of these kind of kernel-based methods as well. So let's assume not only that we have kind of this global representation and a local regression for each site, but let's assume that this is that the matrix that represents them is low rank. Specifically, we're going to assume that our global representation, W, doesn't care about what pixel we're looking at. It only looks at the different bands and merges all the different bands into a single variable, a single scalar, which represents the situation in that pixel. We then have the local representations, which take all the different pixels and integrate that into a single estimate of discharge. This makes sense because how to treat different bands should be the same. The physics is the same everywhere. It doesn't matter where you're looking at, but now that I have a specific river, perhaps seeing water in this pixel is much more indicative of a lot of discharge, for example, if this river is very deep, right? So I want to, per location, treat different locations differently, but the physics of how the bands should interact with water should be at least approximately the same in different locations. The problem is that despite the fact that the model that we're producing will end up being linear, the optimization of this is not linear. We're creating this is a bilinear problem because we have variables that we need to optimize for both in W and in the different V's, and we're multiplying them together. And as we've all learned in our intro to machine learning, before we've learned about deep neural networks, convex optimization is scary. Gladly, though, it's not always scary. And in recent years, there's been a lot of work on low-rank minimization and similar problems, showing that actually, in many of these cases, despite the fact that it's theoretically convex, we can actually do pretty well. And specifically, there's been a lot of work showing how spectral initializations can bring us into the neighborhood of the solution close enough that we know that there are no local minima in the area that we're working on. So what we've shown is that if you take the number of sites that we have and multiplied by the number of samples that we have per site, take the square root, if we have enough of these total samples, regardless of whether they're divided into different sites, then we can find a model that achieves error as low as we would like, depending on exactly how much data we would need. What this means is that we can now create optimal regressions based on many data-starved sites. So despite the fact that in each location we have very little data, we can aggregate those effectively. And just to show an example, so here we're actually looking at two things. So on the x-axis, we have the number of samples we have per site. On the y-axis, we have the number of sites we're looking at. And what you can see here is both that in general, as we increase the number of sites, we reduce So, and sorry, the color is the success rate. So we've synthesized a lot of cases and tried to solve each of them, and the color tells you whether we've succeeded. White means we've always succeeded, and black means we never succeeded. And as you can see, the more sites we have, we can reduce the number of the amount of data we need for each site, and that using the spectral initialization, we across the board can significantly reduce the amount of data that we need. But this, as I just mentioned, is based on synthetic data. So we've produced this information, and actually what I've just said in practice doesn't work. The reason it doesn't work is because all of these kind of low-rank minimization algorithms assume that all of our data is IID, that it's not correlated. And the problem is that satellite images are incredibly correlated. So this completely fails for real-world data. However, we can then, and again, I won't go into technical details, but you can read about it. What we do is we take the original data that we have, we decorrelate it, we apply pretty much the same algorithm that we did before, and then we just need to compensate for that decorrelation that we did. And the result is we get the exact same theorem, but we have this kind of additional constant here that is dependent on the correlations that we have. And obviously, the more correlated they are, the larger the constant. The only assumption we need is that we have a Kronecker covariance structure, which broadly says that much like our bands and pixels, we assume they are kind of independent in some way. We also assume that their covariances are also kind of separable in some manner. This leads to some good results, which I won't dive into because I don't have much time. But just to mention, these results can potentially be generalized to many geospatial applications. Right? The thing that we've assumed here is that we can separate kind of these dimensions of space, which is things are different in different locations, but there are some elements, like the laws of physics, that we assume will be the same in different locations, and we can vastly reduce the amount of data that we need to be able to do that. But we can actually generalize it much further. So as I assume some of you know, in machine learning, solving a new problem is nice, but getting slightly more accuracy on a well-known and well-solved problem is more valuable. So we said, OK, what else can we use this for? And we thought, OK, MNIST is a famous enough example. Could we use this here? And it seems like the answer should be no, because none of the things that we just mentioned apply to MNIST. There's no clear separation between two dimensions. There's like the two spatial dimensions, but it doesn't make sense to say, oh, everything will be the same across the horizontal dimension and so on. It doesn't seem to apply here. And secondly, we don't have a long list of tasks that we can learn together from. But let's try and ask ourselves, OK, let's say we want to use multi-class classification. What if we had a lot of different tasks that were just separating specific classes, so 1 versus 5, 2 versus 7, and so on? OK, so we now have multiple tasks that we can learn on. But we still need to be able to separate our inputs into different dimensions, and the inputs, pixels of an image, are not kind of separable in this manner. One thing we could do is take inspiration from the way convolutional neural networks work. What we know is kind of the standard way in which, when you train a convolutional neural network, the first layer will end up just matching linear patterns against the data, right? That's what we all know, that they kind of match curves or corners or these kinds of conceptual symbols. And then, after it's matched these kinds of different symbols, it'll then utilize those to be able to identify, let's say, the digit 1 and so on. It builds on more complex concepts based on the early kind of linear concepts that it created in the first image. What if we were to say, actually, this is what we want to achieve. We want to be able to say, let's match patterns that are useful, that are relevant to us, to identifying the different digits. And let's call those patterns our W. So our W will define what are the patterns that we are looking for, what are the weights that we have in our first convolutional layer. And then we get a structure that is fairly similar to the bilinear structure we've had before. We need to multiply it by these linear patterns, but then you using different coefficients, those different patterns in different amounts to be able to identify more complex concepts. This ends up working really well, and conceptually is very interesting. So We obviously don't reach the same results you would get with a real convolutional neural network. For example, everything we're doing is linear, obviously, so we can't gain all of the nonlinearity of neural networks. But what you can do is achieve some of that value without the costs, the computational costs, the complexity costs of neural networks. What this means is both a potentially a new way to kind of achieve some of the results with neural networks that are more scalable, and B, perhaps a way to understand at least part of the success of neural networks by understanding this kind of pattern recognition without the complexity of nonlinearity. So after we've generalized, just to go back and remind us why we're all here, the goal eventually is to be able to, using what we've just talked about, create a huge data set that is worldwide and diverse, use that to train hydrologic models using the tools we talked about before, use the results to push into the existing hydraulic models as well as kind of more scalable ones to produce, and be able to produce these alerts anywhere in the world. Thank you very much.
Any questions? Yes.
Yeah, so that's an excellent question. So first of all, there's a lot of work on modeling uncertainty already in kind of classic hydrologic models. The standard way of doing this is using, in hydrology, is using ensembles. So rather than explicitly modeling that uncertainty, perturbating either your inputs or various other things, and then kind of empirically establishing that. We have not done much work on explicitly modeling uncertainty yet, but that's definitely something that we think is important.
Okay, well, a lot of people are getting up. I think it's lunchtime. Let's take that last question, okay.
So do you do any impact analysis in terms of what we're something that with population estimated locations or any kind of infrastructure?
Yeah, so at the moment, we personally don't do that. So we're trying to tackle the modeling itself first before the vulnerability analysis and impact analysis. But that is incredibly important work. It's worth mentioning we're currently putting we're making all of our forecasts and alerts publicly available and in the public domain so that anyone can do whatever they want with this. One of the things we want people to do is to fill in that additional layer of vulnerability analysis and impact analysis.
Okay, with this, I'd like to thank all the morning speakers.